Welcome back to our next exciting installment of Missing Data. I don't know about you, but nothing gets me more pumped than talking about things that aren't there. I do latent variable models for a living, missing data now. So why not, right? Trying to make a guess as to what it is, what things are, data or traits or you name it. So I wanted to start with a couple announcements. First things first, we have a slight change in the schedule. What you can see if you go to well, I can't zoom in too much, but if you go to our course website, February 26th, I'm not going to actually be in the country. I'm actually heading to Germany to meet up with a colleague in a lab. And so I won't have class, but I will provide some material for you to read or to follow along with. And that material will be what I anticipate being introduction to a Bayesian estimation software called JAGS, just another Gibbs sampler. For those of you who have taken my Bayesian class in the last couple years, 2022 or 2024, you'll know I did things exclusively with Stan, but Stan has a problem in that you cannot have a parameter that is categorical or discrete from a discrete distribution. And that's going to cause us problems in imputing or building Bayesian methods for missing data when outcomes are discrete or categorical. So JAGS is something we use. It's a free open source MCMC software package. It's built in, or it's already been installed, excuse me, on the notebook site. So what I actually think that means is most of you will be learning a new Bayes software system. How about that? But that being said, what it does is it uses a different type of a slightly different sampling algorithm. Technically, it's Metropolis Hastings, which is Stan, but the way that the proposal values are drawn are less efficient than Stan, allowing for not having to differentiate a likelihood function. And because of when missing data are involved, those are and Stan would treat those as a parameter. That being a parameter, meaning we wouldn't be able to differentiate it. So there we go. Sound good? So that's it. I've combined a couple classes as well too, but as things go along, I had anticipated trying to teach you from Germany, but then I think the logistics of it just isn't going to work well. I don't know how good the internet system, the center, where I will be is, and then I will be, 7 hours ahead of you, which is fine. I can be happy to stay up till past 10 o'clock teaching. It's just not my best effort, I'm guessing. So anyway, all right. That's announcement number one. Announcement number two. Homework number one is due next Friday. I mentioned in class last week it's a Friday deadline for homeworks, and then I looked at my icon site and I was like, I didn't put a Friday deadline there. So done it next Friday. So up online, you can find it, get it to work. The other thing I would talk about today is that our lecture, homework one involves calculating and estimating semi-partial correlations. The book describes them a little bit, but I'm going to describe them in more detail today. So I added slides to lecture one, and we're going to start there. So at the end of lecture one, I added a few slides about what a semi-partial correlation is, if you don't remember. Um, and then we get into lecture two, which is a little bit of a detour from the rest of missing data, in that lecture two has nothing to do with missing data in a direct sense. Actually, check that. Lecture two has everything to do with missing data, but we don't have missing data in lecture two. Does that make sense? It's the irony of it. We're getting into likelihood estimation, and I want to make sure that we're all on the same page by what we mean by likelihood estimation. And part of that are the building blocks. And so, lecture two is distributions, distribution functions, and types of distributions like joint distributions when you have multiple random variables, marginal distributions, and conditional distributions. Each of those shows up in a different way as we go forward. So, for instance, I mentioned last week maximum likelihood based methods, or I would just say broadly likelihood based methods, not just maximum likelihood, but also Bayesian, are good for missing data. They're good for missing completely at random. That's awesome. But how you go and build those and how you understand those is important as well too. So we're going to describe the nuts and bolts of each of these. We're going to talk about this week. We're going to talk about maximum likelihood and how it works next week. The following week will be how we do maximum likelihood in Lavon, which is a software program that's free and open source and in R. And then we get into Bayesian for what we do. Sounds fun, right? Cool. Questions on any of that? All right. How much ice do you think we're going to get today? I'm going to make a bold prediction, although it's a superstitious prediction, and I have no data to support it. But I will say, because I put class on Zoom, because of the ice, you can pretty much guarantee it's going to completely, somehow, miraculously miss us altogether. That's what's going to happen. Anybody want to guess that's going to happen? And that's not because of any evidence, empirical evidence. That's what I will call the phenomenon known as my luck. Whenever I say preemptively to do something, I speculate wrongly. That happens. Yet here you are trying to listen about missing data for me. All right. All right, let's dive in then. No other questions. Again, the first thing we're getting to today is lecture one. This is kind of a repeat, a little bit of a repeat. No, actually, not a repeat. This is new slides. I just Zoom puts its floating meeting controls right in the corner where like every other program wants to have theirs too. So this is, let me get out of here. All right. We will go down to semi-partial correlations. All right. So the thing that we're talking about, the context of semi-partial correlations for us is with respect to auxiliary variables. Now, remember from last week what auxiliary variables we talk about needing those for, right? So think of it this way. We have y, we want to predict it with x. X and sometimes y have missing data. Okay, so what do we do with that? Well, somehow we need to put x and y into a likelihood function. That's we're going to build to that. But it turns out um, we may have other variables in our data set that relate to the missing data in X. Remember the missing relate that are related to Y, but somehow basically related to missing data in X or Y itself. And because of that, those auxiliary variables will help us achieve a better estimate of our model parameters with the missing data under the assumption of missing at random, right? So auxiliary variables, an important concept. One of the methods that was described at the end of chapter one, and what I use to sort of reinforce that in homework, is the idea of if you have an X and a Y and you have these auxiliary variables, how do you check that the auxiliary variables might matter in your analysis one way or the other? And that's where semi-partial correlation comes from. So that's where we're going to use that. So auxiliary variables, I just mentioned, might mitigate bias and help statistical power when missing data are present. And just remember, an auxiliary variable is an extraneous variable that correlates with missingness in the outcome, but is not part of the main analysis, right? So the outcome here is y. If we have x predicting y, but we also have missing data in y, can we use some other variable that might also predict y to help us understand a little bit more of why things are missing, or better yet, what those missing values might be? Um, a key aspect of variable selection is understanding their semi-partial correlation with the outcome, right? So semi-partial correlation is a correlation that quantifies the unique contributor of a predictor to the outcome after removing that shared variance between the auxiliary variable and other predictors. So you may think about this. Remember in linear models, in a multiple regression, right? We have y being predicted by x and z, right? That model, we talk about z predicting y, but controlling for the presence of x, right? So what a semi-partial correlation is takes that idea, which basically saying um, the regression line itself is quantifying the impact of z on y, right? The slope of z predicting y, controlling for x. Well, we want to change that slope into something that's a little more familiar, or something like a correlation itself. So semi-partial correlations run in that way. Turns out they're really heavily tied to linear models, so we're going to see that as well too. Any questions about any of this? And by the way, I'm sorry I have to turn my eyes away from the camera to look at you, but this helps you stay off camera. So there we go. So semi-partial, I just mentioned this, unique association. You may understand partial correlation as well, right? So the difference between semi-partial and partial is sort of in the idea that we need partial of a partial, right? Anyway, if you have variable x, variable y, and some, I'll just say some auxiliary variable a, right? If you want the semi-partial correlation of a with y controlling for x, what you're doing is controlling for the overlap of information between a and x on y, right? But y you're not controlling for at all. The alternative of that is a partial correlation where you're controlling for the impact of a and x and controlling for the impact of a and y. So basically, excuse me, x and y and x and a. So basically taking x out of both sides of the equation. So partial correlations, we end up having a lot more. I got to tell you, when I was in linear models, I don't know about you, I learned all this stuff. It was 1990s, right? And sounded good. I felt like I studied hard. I got it. And honestly, I don't know how much, unless I teach a linear models course, I don't ever talk about this stuff very much anymore. So this is a little rusty information for me. I don't know about you. Did you learn this in your linear models when you talk about partial and part correlations? Ever heard those terms before? Yeah. Well, if you're like me, you may have learned them and then promptly forgot them. So, but let's talk a little bit more about it. Semi-partial correlation is also known as a part correlation, right? So remember, partial correlation removes the influence of x on a and the influence of x on y. The part correlation or semi-partial correlation removes the influence of x on a, but not the influence of x on y. All right, so here's a formula for how we do that. Actually, I just said A. Let's call x1 what I called x before, and x2 what I called A. So if we want the semi-partial correlation, in this case of x1 with y, controlling for x2, we calculate that by a series of these correlation coefficients. These are all Pearson correlation coefficients, by the way, right? R x y R between x and y1 is the correlation between y and x1, the straight Pearson correlation, no partial involved at all. R y and x2 is now the correlation between y and x2, and then R x1 x2 is the correlation between x1 and x2, right? So we take our correlation between our one desired part, x1, and the other, y. We subtract from it the correlation of y with the auxiliary variable, or the thing we want to control for, x2, times the correlation of x1 with x2. And we divide that whole thing by the square root of 1 minus r squared, right? So that correlation squared between x1 and x2. So this is your formula for it. Sometimes it's denoted as y, r with y, x1. So you read this as the semi-partial correlation of y and x1, where we're controlling for x2 on x1 only, right there in the parentheses, right? So what does this tell us, right? That tells us things like this. If we were to create a regression where y was being predicted by x2, and then we wanted to think about adding x1 to that analysis, this semi-partial correlation would tell us whether or not that regression coefficient would be bigger than zero, right? So basically it's saying, after we control for predicting y with x2, does x1 help us in our prediction more than just x2 by itself? Does that make sense? Okay. So if this is non-zero, it means, hey, x1's needed in our regression function, in our linear model. If it's equal to zero, we can think x1 is redundant with x2 in predicting y, and therefore it's not needed in describing the model itself. How are we doing? Okay. So you can see where we're going with this now, right? If auxiliary variables are related to the outcome, but maybe not needed in the model, we can find a way to put them into the likelihood function if we calculate semi-partial correlations with those and the outcome, controlling for the other variables that are in the model as well too. And that's the concept of what do we add for auxiliary variables? Because auxiliary variables is one of our first steps in modeling it, missing data, handling missing data. Now you might be asking me, thinking to yourself, what if I don't have auxiliary variables? Well, got to make sure all your other variables are in the likelihood anyway, and that's still going to be related to what we do here as well too. Okay. All right. So why is this important? I put these slides together, and here I told you before. Um, Understanding the unique contribution, right, of each variable. In feature, if you're in machine learning or predictive modeling, you can use semi-partial correlations to figure out which features tend to predict outcomes a little bit more. Although I will say machine learning, even though everybody talks about it, the very first version of machine learning is regression. It is. So don't forget that. Um, for model interpretation, you can talk about the relative importance of predictors. You can help you compare multiple predictors, which may have the most unique explanatory power. So this idea is that because the semi-partial correlation removes shared variance from only the predictor, it reflects the real-world scenario where some predictors contribute uniquely to an outcome while sharing the variance with others. So with missing data, we use this for auxiliary variables. It helps us to figure out which auxiliary variables we might want to include in our analysis. So the things that you're doing in homework this week, you've got three auxiliary variables. You've got an X, you've got a Y. You want to figure out which one of those auxiliary variables might be needed to be put into the analysis by understanding which one of those relates to Y itself. Cool. So I'm going to give you an example of the semi-partial correlation and how we can compute it. The first example I should have done first, but I'm going to create a data set, right? This data set has 100 observations. We have a Y, we have an X1, we have an X2, right? And then we have an auxiliary variable, X1, auxiliary variable that is related to Y, X1, X2, and has some other type of error as well too. Right? So this is now saying this auxiliary variable is going to be related to Y. That's what this is telling us. So if we wanted to look at, here, let me go flip to R real quick because this will help a little bit more. So how's my font on my screen? Is it big enough for you to be able to read? How is that? Is that better? Okay. Sorry about that. All right. So this is the set of code I just had. Here's my data. There we go. There's our data. Uh, so the way that we could compute an auxiliary variable, semi-partial correlation, there's two methods. One is use a package, spcore. This is much more rigid, but it works just fine for your homework assignment. But because I have two other variables of interest here, x1 and x2, spcore becomes more difficult to use. So what I'm going to actually do is compute it the old-fashioned way. I don't know about old-fashioned, the little bit less um, convenient way, but it helps understand the concept, right? The first step is to form a regression where we're predicting the auxiliary variable with x1 and x2, right? So if I were to do that right here, you would see this function. And if I really wanted to, oops, show you this, you'd see this, right? There's a significant impact of x1 and x2 on the auxiliary variable. So why I did that is because the residuals of predicting the auxiliary variable are actually the amount left over after we explain it with x1 and x2. So when you think of the semi-partial correlation, right, we're wanting the correlation between the auxiliary variable and y. Once we control for x1 and x2 on the auxiliary variable, it turns out these residuals are our key to removing x1 and x2 from the auxiliary variable, right? So this ox resid right here literally is what's left over after we control for x1 and x2 on the auxiliary part. So now, wouldn't you guess that the correlation between the partial correlation turns out if we take those residuals and correlate it with our observed data for y, we end up with our semi-partial correlation coefficient, 0.33. Right. So what we've done is, right, instead of looking at the correlation between uh, data and y, right? That's 0.15, right? The correlation for auxiliary residual and the data, sorry, this is auxiliary in Y, controls for the impact of X1 and X2 on Y, removing them from it. And what's left over is this semi-partial value of 0.33. Now, whether that not that's enough, I don't know. I don't have a p-value with this. I probably could calculate a p-value if I really wanted to. Um, p-values only get us so far anyway. I was just going to see if I could do this, but I don't think I can. Nope. There we go. Didn't do much good at it, did it? Anyway, but let's imagine this 0.33 was significant. We would want to include auxiliary in our analysis. That's what's telling us. Questions on any of that? Yeah. Nope, that's not what I want. This one. There we go. That's it, that right there. Okay. We can do the same thing with the SP core package, but what ends up happening is um, the correlation is with the value of the row and the first column controlling for the other values. Actually, yeah, there we go. Controlling for the other columns, right? And so we do have the 0.33 right there. We can include it. It is right there, at least. So we do see that one. However, and hey, look, there's a p-value for it. It's significant. Yay. There we go. And this, I believe if I'm not correct, it's the R to Z transformation that give you that p-value in correlation. Gosh, it's been a long time since I taught linear models. Anyway, there you have it. That is auxiliary. Your homework will run just fine using the SP core package. If you want a challenge, you can try the residualizing value version that I told you in LM. If you wanted to try it, both are should give you the same numbers. You should be able to see whether or not you end up getting there. But that's basically it. Questions on semi-partials? Okay. Yes. Question. Unfortunately, no. In a frequentist perspective, we often think the p-value will help us as a cut point. So if an auxiliary variable is significantly related to the outcome after controlling for the other variables in the analysis, we would say we want to include it. Maybe not necessarily in our model, but perhaps in our overall model likelihood to help us with missing data protection. Does that make sense? That's what I would typically see in a frequentist setting, yes. Um, that being said, you can know where that goes, right? If you're in a situation where you have lots of data, and these days many people have lots of data, you probably would some type of R squared. Basically, could you square that and describe how large it would be um, otherwise, right? Basically, what is its effect size? So and if you switch to effect size, if your p-value is not enough, you can switch to basically the same rules that you would talk about with effect size for correlation or R squared, I think are a good guideline for it, although I'm not an expert as to knowing what that level happens to be. And I will tell you, as you get into auxiliary variables, there are situations, I don't know how your data look, but in a lot of the studies I've worked with, you collect a lot of data just because, when you have access to a participant in your study, you want to get as much from them as you possibly can. So in theory, you may have a ton of auxiliary variables. The question is, in the book, and Craig talks about, the ones that tend to have the strongest semi-partial correlation. You get two or three of those, and you quickly get like a diminishing return on how much they change the analysis. Alternatively, Craig talks about building, if you have, again, hundreds of auxiliary variables, you could then use a dimensionality reduction on those, right? You could take a principal component of the auxiliary variables, for instance, and put that in the analysis as well. Again, this is not directly going to be in your model of X1 and X2 predicting Y. It's going to be in a likelihood function trying to help you control for that variable when missing data are present, right? So when you put in a principal component, right? The principal component is a linear combination of all the auxiliary variables weighted by values such that the principal component has the first principal component has the most variance accounted for, shared variance in it, right? And so that way, that number goes in analysis. Often we lose all possible meaning for what that means in a reality, like in a model-based sense, if we were to model Y with principal component itself. But it does give you a combination of auxiliary variables to sort of give you the most bang benefit without having 100 of them in the analysis. Because again, it starts to get unwieldy after you get too many. Okay, questions on any of this? Any more? Any other questions? Another question in the chat. Yeah, JC, go ahead, please. Yeah, I maybe I didn't know that. Let's find out. Uh, okay, okay, right there. Nope. X equals, actually, yes, that should give you, let's take a look. Calculate okay, so it will give you your semi-partial correlation. It also gives you a p-value as well as statistic. And so here, I think this is just, you specify the X and specify the Y, which would be good in this case. Um, the input to it is, let's see here. I'm assuming it doesn't even say directly, but it looks like you're controlling for the correlation between X and Y, controlling X for Z is what I'm assuming is happening, although it doesn't necessarily tell you what X, Y, and Z are here. So, yeah, I think that could work. I will tell you the SP core function by itself does give you this same result, but it does it for all combinations of variables, right? So you'd say this is the semi-partial correlation of x1 and y controlling x1 with for x2 and auxiliary. So it sort of gives you all of it plus the p-value as well too. So I'd like to say both give you the same information. One is more direct, like to your specific situation. One is more here's all the variables themselves. Does that help, JC? Thank you. Ahmed writes in the chat, in our example, we can use linear regression coefficient B3 to get the partial correlation. Yeah, you should be able to, right? That should be able to be rescaled itself. Um, the relationship, basically that regression coefficient, if we put that into a model with x1, x2, and auxiliary predicting y, that is a non correlation version of the coefficient. The issue is how do you convert that into correlation? But if you were looking for parameter value and significance, that should give it to you the same way. So good point. Thank you. Other thoughts? How'd I do for not teaching that in like 17 years? It's okay. You can tell me it's not good. I I don't. I promise to be fair. Vladimir. Oh, um, I believe they should be independently, but if you put them together, I can see them sequentially. Let's put it that way, right? You can put one in, and if it's significant, I could see you could add the next. Um, why I'm hesitating is if the two variables are highly correlated to each other, but not to the x variables, they'll cancel each other out if you put them in together. If I'm not mistaken, right? And so that that could be problematic. So you know, I guess I'm saying I don't have a great analysis strategy. My personal way of doing this would be more of a sequential. I put one in. If it's significant, then I put another one in. or if it needs to be there, right? So I keep adding information. But the more auxiliary variables I add to the semi-partial correlation, when I'm controlling for that from other ones, that again, that diminishing return happens right away, right? So the one that has the highest correlation with y will probably overlap the other auxiliary variables as well too. Does that help? Am I making sense with how I'm saying that? All right. Other questions? Okay, so last question to you is why is this important again in missing data? I'll ask you that. I might have just said it 3 times, but I want you to repeat it to me. One of you. Put another way, why am I showing this to you in class? That's right. So we understand which auxiliary variables are related to our outcome with missing data, and thereby being able to keep those add those variables to an analysis that involves it in the likelihood, maybe not necessarily in the model itself. Thank you, and thanks for very well put. Very good job. Okay, shall I move on? Do to the next chapter. All right. It's funny. I was reading the book, and I I realized a lot of the way the book is sort of outlined is sort of how I have built a previous class. And so I have a bunch of slides, and that's what I'm going to start with. So I'm not in R Quarto here because converting my PowerPoint slides to Quarto is a pain. So I'm just in PowerPoint. But it's interesting because I'm like, oh, I haven't told you about that. I want to tell you about that. Where have I built lectures for? And sure enough, um, way back in 2012, I moved from University of Georgia to Lincoln, Nebraska. There was this Lisa Hoffman person I was dating at the time, and I thought it'd be easier to go live with her rather than um, visit every so often, as you might imagine. And so moved there, and that semester we team taught a course called, at the time, multivariate. And multivariate is an interesting course. We have one here. Multivariate in many different institutions varies widely, right? There's a famous multivariate book by authors Tabachnik and Fidel, who were at a California State University campus. That campus, I believe, is Northridge, CSU Northridge. They didn't have PhD program. Most CSU campuses don't. They are masters only. I'm a graduate of Sacramento State. I know one of you who will go unnamed is also a graduate of a CSU campus as well. There may be more of you who've been there as well. But that being said, knowing that, when you read the multivariate book by Tabachnik and Fidel, you get things like logistic regression or places that you wouldn't see it. Well, then the other flavor of multivariate is like I took at Illinois, which is matrix algebra, multivariate normal distribution, and then a whole bunch of methods that honestly we don't use a whole lot in research anymore. They've been subsumed by more modern methods. And what I mean by that is, the first class I ever taught at a grad school, there's a point to the story, I promise. First class I ever taught at a grad school, spring or fall 2025, oh, 20 years ago, seriously, fall 2005, was multivariate. And I used the book I had in grad school, a book by Johnson and Wickern. I liked the book. And I went through, I did the matrix algebra, multivariate normal, and then we started getting into multivariate statistics like Hotelling's t squared, multivariate analysis of variance, multivariate regression, principal components analysis, canonical correlation. Stop me if you've heard these terms before, right? So, didn't teach the class for 6 years. Then I taught the class in summer at Michigan. The University of Michigan has a summer program for the ICPSR Intra University Consortium on Social and Political Research. That got to teach a class that was multivariate. So I went back to my multivariate slides, and as I'm putting this together the class, I'm like, I've never used any of these methods that I taught the first time I taught the class. And of course, Lisa was also teaching at that time at Michigan. And so we had this conversation about what should multivariate look like? And that's what sort of became what we called the bridge course. So the fall 2012 course was the third course in a sequence of sort of stats classes in the psych department. And what we wanted to get across was, you've taken linear models. They had basically linear models in the first year, regression and then analysis of variance. But there's a big jump between those methods and when you get into multi-level models or mixed models or structural equation models or IRT models, right? It's almost like those other classes of models ran on a whole different system. I can remember going to proc mixed before, going into mixed models and being shocked I couldn't find the sums of squares table. Where'd that go? Well, it turns out estimation with maximum likelihood. So a lot of this bridge course became how likelihoods work, likelihood estimation functions, um, generalized models, right? So what Lisa teaches in the generalized class was the portion of the class that we brought from generalized models. We called it sort of this building blocks approach to looking at statistics. Well, it's funny. Craig's first book was 2010. I'm pretty sure I was heavily influenced by him at that time too. And so, part of that class we had a missing data unit, but we were building up to getting to missing data by describing these properties. And it turns out, as I'm reading the second edition of his book now, I'm like, yeah, all of this is needed to understand missing data better. So that's why I'm in this. It's a long history. That's why the slides look the way they do. But I think you'll forgive me on that. It saved a heck of a lot of time, and I like this lecture. So if you wanted it all to be Quarto, I'm sorry. I'll just apologize now. So there's my story. Interesting. I know. I'm an old man. All right. I'm an old man. It happens. I got to tell stories. All right. So this class today is a primer on mathematical statistics, univariate distribution, the normal distribution, and then putting it in the context of models. Right. So none of this has missing data, although I do have the IQ and performance, I think, is part. No, actually, that's not in this lecture. Anyway, all of these are involved in missing data, but none of them specifically have missing data today. This is to give you information on what it means with the likelihood function itself. Okay. All right. So the building blocks, the basics of math stats, random variables. What is a random variable? The types of random variables exist. We'll talk about univariate distributions, so some general terminology about what distributions are, what they need to look like, and then types like univariate normal or other popular univariate distributions. We'll also get into types of distributions that are marginal, conditional, and joint, right? So these are important in missing data. Will become more important in missing data because if you take what I just stopped talking you, for instance, if I tell you the linear model, that describes a conditional distribution. Conditional, right? So basically, we're looking at what's the distribution of y conditional on values of x, or x1 and x2, right? But that conditional distribution, you can actually rephrase it as a joint distribution. That joint distribution is important because it is what gives you missing data protection in a package like Lavon, a maximum likelihood linear model type package. So understanding some of these values is important. Definition is important. Furthermore, as you get further in the book, you'll see that one of the methods for controlling for missing data, joint distributions can be very difficult to specify, but you can always factor them into a series of products of conditional and potentially marginal distributions as well, too. And those conditional and marginal distributions are often much easier to work with. This is a concept that I had to deal with yesterday. Let me see here. At least two of you who will go nameless are involved in a project with me for an NCME symposium. And one of the papers is going to rely upon having a multivariate truncated normal distribution, which is really difficult to do. But I believe I can break that into a series of marginal and conditional distributions, which will be much easier. So interesting. It shows up a lot. And again, just like it's not going to ICE today because I've had class on Zoom, when I was a student and I was taking classes like this where I'm like, yeah, I'm never going to need to know this, particularly in mathematical statistics, it was less than 6 months later where I was like, I really wish I would have paid more attention when that happened. So I'm going to try to give you all that today. Cool? I hope. And if it's not, just fine. I understand. We'll get through it. Thanks for being here. Um, Other things. Okay, so Talk about expected values, what means, variances, and the algebra expectations gives us, because sometimes we have linear combinations of things and linear combinations of random variables as well. And then sort of to provide, so all of this stuff, the building blocks are sort of without context. They just exist in mathematics, but they all have direct ties to things that you know, particularly about like general linear model. So I'm going to put these ideas to use in a general linear model to describe why they show up, and they sort of permeate statistics. They're the next layer of understanding statistics beyond just getting a software to work. Understanding a p-value this is sort of the next step going forward. All right, so let's talk about random variables. By the way, I didn't mention this at the top. Breaks will still be at the same time, 120 and 220, so you can plan accordingly for about 10 minutes. Anyway, random variables and statistical distributions. Start on that. What's the random variable? Let's do this. You can see where I'm pointing now. A random variable is the term random. Random is certain situations in which the certainty of the outcome is unknown and is at least in part due to chance, right? Rolling the dice. Error in a regression model, right? Sort of that uncertainty is not there. And then variable is a value that may change given the scope of a given problem or a set of operations, right? So putting it together, a random variable is a variable whose outcome depends on chance. Possible values might represent the possible outcomes of a yet to be formed experiment, right? So thinking about that, I might define a random variable as x, lowercase x right here, and I'm going to describe a little bit more about what that means as I go forward, right? So actually, let me just stop right here. What do I mean by x? All right, so let's imagine I say x is the number showing on the roll of a six-sided die. That would fit the definition of random variable because number one, we know that rolling the die, I don't know yet of a model that would tell you uh, uh, basically there was a lot of uncertainty as to what number lands up top, right? So it's random. And the values of x differ, right? There's six different values a six-sided die can give you. So it's random. Those values will differ. And if we keep repeatedly throwing it, we see different numbers that show up. That is called a random variable, right? Now, if I loaded that die and you kept rolling it over and over and over again, and all it kept showing was number one, would that be a random variable? Can't be. Because, well, let's put it this way. That's what statistics are for. We're going to go calculate the probability that you observe a one multiple times by chance. You'd have to have a model for what it should be. But what if every side of the die was just the number one and you could look at it and see it? Then you would certainly know what the outcome would be. It always would be a one. And because that value didn't change, it's a constant. So it couldn't be a random variable. It's not random because you know, for instance, one of those six sides is going to be landing face up. So you know that there's the random process happens, but it's always the same number that's pointing up. And that number, since it's always the same, is not a variable at all. So does that help a little bit? Random variable? In our data, random variable, usually what we're modeling, y in a linear model is a random variable. Right? All right. Types of random variables. So I just mentioned rolling a die. That's one type of a random variable in that it is discrete. That's point two here, right? Sometimes called categorical, right? So X could be a person's gender. You draw a person at random from, some population. Like, let's imagine you say, I'm going to randomly find a student on campus at 12:20 today. The gender of that person is random, right? Because if you do that same process at 12:25, the gender of the next person might be something different. It's a random variable. So that's a very discrete random variable. The other distinction we make is continuous. Now, I want to note to you, continuous in some ways exists in a fantasy world because the probability of observing any one discrete value is zero. But let me get to that. An example of continuous random variable, x could be the height of a person drawn at random, right? Height in centimeters or inches, whatever you prefer. That if you did that same experiment, let's take one student we randomly see on campus at 12:20, you get their height in inches. And then at 1225, you get the height in inches. Those are random variables, right? They're continuous, or at least plausibly continuous, because they're not obviously in categories, right? And then finally, why an outcome in a GLM might be random. Well, we say that because if you look at the model equation for regression, there's error, and error has a normal distribution. So y, therefore, has a random component, and we're quantifying how much uncertainty we know about y with it, fitting the definition of random, right? And because y varies, it makes it a variable. Now, I mentioned continuous, there's this one catch. So when we define continuous distributions in statistics, right, to calculate the probability of any event occurring, we take the distribution function, which we'll hear about more, and we integrate it within a bound, right? So the probability of someone's height being between 50 and 60 inches, if we had a distributional, continuous distribution for that, we could take the integral between 50 and 60 in calculus, get the area under that curve, give that to you. But that poses a bit of a problem in that in our continuous data, the integral, there's one quirk of calculus that an integral, the limits of integration, when the limits are the same, the integral by definition is zero, basically saying there's no area to a single line, right? And so what we have to do to that, so that what if you play that out in process without a small adjustment to thinking about what that means, you'd say the actual probability of observing any given one height is close to zero. But the way we get around that is by saying, okay, when we observe a person's height, there might be some tolerance around a number that's within error, right? It's the precision of like a measuring tape or precision of an instrument that measures, right? And that would be the limits of our integration, giving us that value itself. So if I said somebody is 64 inches tall, really, if we look at the way that we measured that person, there might be something like, a thousandth of an inch wiggle room around it. That gives us the probability of observing the event. So a little bit of a nuance there, but I know some of you are in that spot where nuances are very important. Okay, next, we could have a mixture of discrete and continuous variables, right? So for instance, X could represent a person's response time, and I thought I fixed this, but it should be if greater than 0 and 45 seconds. So somewhere between 0 and 45 seconds. Hearing that? So you present a task on a screen, a person's supposed to hit a button as to which maybe it's a show me which letter appears. Tell me if you see the letter S or the letter T and you clutter the screen with a series of other letters and you see how long it takes them to press the S or the T, that's a response time. But if they take more than 45 seconds, they've sort of kind of forgotten the task or maybe ignored the computer, so we might want to code them as a zero. So that value itself, zero right here, although I could probably give it a different code, like a -1 or -2 or something like that, doesn't really mean anything numerically, but it's a discrete category, right? So if you responded within 45 seconds, you get the number. If you didn't, you get some other categorization, right? That is an indicator of a nature of a mixture variable. How's that sound? Cool. Other questions? One question would be, why didn't I look at the time? I just love random variables so much. How about we pause here and take 10 minutes for break? I'll be back at 1:32. I may be back before that, but if my uh, uh, video and audio are off, you'll know that I'm not at the computer. Okay? All right. We'll see you in about 10 minutes. Thank you. And let's keep going on. All right, so the key features of random variables. We just talked about three types of random variables. There are some key features that show up in multiple random variables as you go through the process of describing them. Random variables are each described by something called a probability density function or a probability mass function. Sometimes referred to PDF for probability density function, PMF for probability mass function. What that function indicates, particularly for a PDF, is the relative frequency of an observation occurring, right? In a probability mass function, that function indicates the probability an event will occur, right? So PMF is for discrete distributions, PDF is for continuous. Both are mathematical functions that give a rough picture of the distribution from which a random variable is thought to come from. Right? So the type of random variable dictates the name and the nature of these functions, right? So for a continuous random variable, f of x is called a PDF. I just mentioned that. The key thing about the PDF is that the area under the curve must equal 1. It's sort of that is our foundation to describe that as a probability mass, because probability has to you cannot have a probability greater than 1, right? That area under the curve again is comes from calculus using integration. Right? So integration is this process of describing the area under a curve. If you were to plot the curve, which we'll do in just a few slides, the height of the curve will tell you how likely x is. Right? So if x is your random variable and f of x is its distribution, if you plug x into the PDF, it returns a number. That number is the height of the curve, which is any positive number really, and it's called the relative likelihood of an observation occurring. The number itself, again, can be any real number. It can be any positive number, right? So you could have a likelihood value of 22, and in some distributions you might get that, right? It's not a probability though, right? So you have to remember that. It is the basis of likelihood theory though, right? It's the relative likelihood. We're going to talk more about that in just a few slides, what that means. For discrete random variables, f of x again is the probability mass function, or PMF, and the sum of each of the probabilities, the probability for each of the discrete cases, the sample space, must equal 1, right? Again, a probability measure. And the function is a probability, right? So the return value, if you plug x into the function, the number that comes back will be between 0 and 1, right? So the difference between the two is in a discrete random variable, you get a probability out. In a continuous random variable, you get a likelihood or relative likelihood out. Now, what about mixtures? Those are special cases, and there's all sorts of weirdness involved in that. So I'm going to stop that right there. We won't have mixtures in our value in our what we're going to do for what we have right here as well too. All right. So other key terms that we need to define. Number one is the sample space. Right. The sample space is the set of all values that a random variable can take. Right. So this is a mathematical definition. Every defined distribution, right? So a normal distribution, for instance, or a Bernoulli distribution, they have each random variable has to be within the range of the sample space. So if you say that a random variable x comes from a normal distribution, right, which is denoted as x, this little tilde right there means colloquially comes from, or another way of describing that is follows. If you're into the statistical definition, sometimes we describe this tilde as meaning IID, which is independent and identically distributed as. That's way too like deep into the math stat. I'm trying to keep this a little more high level, even by giving you just a primer on it, right? So when you see x tilde n, that means x follows a normal distribution, and then you have to remember that the normal distribution has two variables to describe it in a univariate normal distribution: a mean x and a variance sigma squared. I'm sorry, a mean mu, variance sigma squared, both subscripted x here. But if you say that, then x actually can follow the sample space for the normal distribution is negative infinity to positive infinity, which is what we would say is the real number line. So if you say x follows a normal distribution, what you're saying is it's plausible that x could take values anywhere on the number line. Now, that's the strict definition. In practice, um, the normal distribution of the bell curve, you're familiar with that. As you get further and further away from the mean, the likelihood of observing any event is so infinitesimally small that the normal distribution is often used in cases where the sample space is not necessarily negative infinity to positive infinity. For instance, if I wanted to model heights, we know that nobody can be negative inches tall, right? And we haven't yet observed somebody whose height is close to infinite, right? So, but in the narrow range of human heights or things that we might collect, a normal distribution may describe that very well, because once you get out of 4 or 5 standard deviations from the mean, it's very unlikely to observe anything, right? Okay. Similarly, for the sample space for a random variable representing the outcome of a flipping of a coin, right? Heads or tails. This is denoted as a set, H or T, right there. Right, so it can be there. Or similarly, if you have a die that has six sides and each side has a different number on it, the sample space for a random variable representing the outcome of a roll of the die is that set 1, 2, 3, 4, 5, 6. That makes sense? Sample space is sometimes called support as well, the support of the distribution, if you've heard that term before. So if we were to use generalized models, so I'm in generalized, maybe you've taken the class, Lisa Hoffman teaches it here, called generalized, right? If we have a linear model, we say y basically follows a conditional normal distribution because y is thought to be plausibly continuous or roughly continuous. But if you are predicting an outcome like a count or um, the probability somebody who answers a question correctly on an exam, those are not normal. You can't use a normal distribution for those. They're discrete distributions. So one of the tricks in using models, generalized or otherwise, is when you specify a random variable, you have to specify a distribution for it. And if you're not familiar with which distribution to use, that's sort of the trick in learning modeling. But generally speaking, you want to pick a distribution where the sample space of your outcome matches the sample space assumed by the distribution, right? Again, there are some exceptions. Normal is used for many things that are plausibly continuous. But if you have, if you're modeling the probability someone answers an item right on an exam, normal isn't going to work well for that for several reasons. So, questions on any of this? Any questions? Moving on then. All right, so we use statistics, distributions, and data analysis all the time, right? We use these to make distributions. We basically where they show up are distributional assumptions on various parts or parameters in our model, right? And those assumptions themselves govern how we estimate our models. Right? Turns out the distribution, I mentioned it just a couple slides ago, the height of a distribution function for a given value is a likelihood or a relative likelihood. It's the core of likelihood theory. So what we end up doing once we define a distribution is that we can actually define a likelihood function based on our data. And that's what we can use to estimate models. We can then, or alternatively, we may even understand a bit more about distributions are actually ubiquitous. Like if you use maximum likelihood, then there are certain properties of ML estimates that we'll get into a couple of weeks where you can say as n goes to infinity, we can use the idea of what distribution that result converges to come up and give us inferences on values in our model, such as standard errors, walled tests, key values on walled tests on parameters, the things that you would see in a table of parameters from an output of a linear model. And finally, this class, how missing data may be used or modeled or imputed even, right? So distributions are sort of the core of everything we do in statistics. And so likewise, if you have to make an assumption about distributions, it's just that, it's an assumption. And if data don't follow your assumed distribution, inferences may end up being inaccurate, right? So if you use, let's imagine that this random variable x is the Likert score of an item asking you how happy you are that it's going to have ice, that the ice storm is going to hit today, right? Where one represents absolutely unhappy and six is absolutely happy, and some scale in between there, right? If I decided to take that and model it with a normal distribution, the value, how well I approximate that distribution depends on the shape of those probabilities and how well the normal can incorporate that in its curve, right? And sometimes it's really well. We know a normal distribution. We know that bell curve is single peaked. It's unimodal, right? So if you end up seeing that people are neither happy nor sad that it's going to ice today, they right here, but there's very few people in the tails. Sounds good. But if it's how I'd like to think it is, because I'm sort of projecting my opinion onto everybody else, then there'd be a big pile of ones and very few values everywhere else. And that would really not work with a normal distribution very well because it's a heavily skewed distribution within its sample space. Does that make sense? Cool. So it can be important to check distributional assumptions while running statistical analyses. I wouldn't say prior. Many of our models, I do say prior in here, but I would let me qualify that. Prior, eh, this is a sort of a pet peeve of mine when it comes to intro classes. Sometimes you'll have people saying, "Hey, check that your data are normal," right? And they'll teach you methods for doing that. But why do your data need to be normal? It only matters when you start to put a model together where you need to worry about that. And you may say, "Wait, in regression, there's error at the end of the line, right?" Yes, but if you, what I'm going to show you today and then later on is that means y is conditionally normal, meaning after you control for x, what's left over should be normal. That's not your data. So if you just transform y ahead of time, not a good situation. So I should really change this to say checking for distributional assumptions in statistical analysis is important. Checking a priori and then transforming your data under some ideal is actually a model-based approach, but the model is fairly naive, very kind of not a good model at all. An empty model is really what it is. Cool. All right. Let's talk about some continuous univariate distributions. I'll talk about three: a uniform distribution, normal distribution, the chi-square distribution. This is just to describe to you what distributions do and how they work, and to get the sense that even though these are three different distributions, each of them has a PDF. Each of those PDFs gives you a relative likelihood, but each of those PDFs also depends on the set of parameters themselves. That's what we end up using. All right. So those parameters of these distributions um, sometimes get constraints put onto them based on hypothetical effects in data. So, for instance, I mentioned y is conditionally normal in a regression, a linear model or linear regression. The mean of y in a normal distribution, the mean is actually regressed upon the regressors themselves, the x's. Right. So what the mean of y will happen to be is your predicted value for y in that sense. And so those are types of constraints that we take hypothesized relationships and quantify them with parameters. Well, let's start with uniform. Any of you seen a uniform distribution before? I'm sure many of you have. It's pretty boring, but it serves as a very good baseline. Uniform distributions, um, the uniform distribution PDF is 1 minus the parameter b minus a. So what we would say is the uniform, or if a random variable x follows a uniform distribution, it would look like this down at the bottom. X tilde u for uniform, and then the two values it takes are parameters, a and b. A is the lower limit, b is the upper limit, right? So what we're saying is, number one, what is the sample space? Let me ask you this. What is the sample space of x if we say it's uniform? Or the support. Sample space and support are synonyms. Yes. The sample space is literally the number line between A and B itself. So if we have a set of variables, we have heights and we observe heights between 60 and, I don't know, 76 inches or something like that, or 55 to 80 inches. We put a uniform distribution, trying to build a model with a uniform distribution. Um, if A and B are too small, it's not going to fit at all, right? We're going to have extra data on the side, so we don't even know what to do with that. So if an observation comes outside of the sample space, the likelihood is just zero at all for it, right? It just cannot happen. But within the range of A to B, right, this forms a rectangle, right? The uniform distribution forms a rectangle in that the height is equal for any value within A and B. So putting that in the context of what's more likely, it says every value between A and B is equally likely to be observed, right? So if you were to go look for data like this, I don't even know what you'd find in a regular, you know, sense. Uniform distributions are sort of rarely used in inferential statistics, but it's basically saying, yeah, nothing's more likely than anything else. They're all. It's almost like a random chance you draw any number between those two. Similarly, the uniform distribution is nice because we can see that the area under the curve is 1 without having to use an integral, although we could use an integral if you wanted to. But we can think about it this way. This distribution function forms a rectangle, right? And we know that the area of a rectangle is length times width, right? Should be. I think it is. All right. So in our case, height times width or something like that, right? So what is the height of it? It's b minus a. Uh, oh, sorry, 1 over b minus a. What is the width of it? It's b minus a. So b minus a times 1 over b minus a gives us a value of 1. That's it. So this distribution sort of has all the features that all the distributions that we know about exist, but it's very simple, it's very easy to see. And we rarely use it in inferential statistics. Sound good? Although in Bayesian statistics, using a uniform prior is totally legit. You just have to make sure that your width of the uniform prior includes all the values a parameter might be. All right. Here is an example of PDFs, right? So this distribution function is 1 over b minus a, here's some examples of values. So if a and b were both 0 and 1 respectively, and I plugged in a 0.5, the value of the height would be 1 for 0.5 and would be 1 for 0.75. And so because these both come from the same exact distribution with the same exact parameter, we say both are equally likely because the value that returned is 1. Similarly, though, if we change the limits, if we had a value between 0 and 20, we find a 15, we know that's 0.05, and then every value that comes from that distribution will be 0.05. But we can't really compare 0.05 with 1 because the values of the parameters have shifted. So it's no longer relative anymore. It's sort of irrespective of the difference. And similarly, we plug a 15 in and the limits of the limits of the distribution are 10 to 20, that value is a 1. Each one of these is likelihoods. So again, it's just underscoring that the feature of a uniform distribution that all values in the sample space are equally likely. So you don't see, right? Similarly, you can actually do some computation here. The mean of the uniform distribution, we could probably figure that out, right? If we know that the area is 1, like basically 1 half a plus b turns out to be the mean, right? Sort of right in the middle, the midpoint of it. And then the rest of it, the variance, technically speaking, the mean is found through something called the algebra of expectations we'll talk about in a bit, but the variance of that is also found by the algebra of expectations. So there's this mathematical formulation actually involving an integral. This thing is 1 over 12 times b minus a squared. And this brings up a point that I always think is funny in statistics. Whenever you see like a denominator or something in a radical that's like a weird number, like how did that get there? Is what I want to know. You ever think that? Like 1 over 12, yeah, there we go. Or like in logistic regression, if you look at an error of a logistic distribution, it's pi squared over 3. It seems oddly specific. Well, there you have it. Are we good on uniform? Cool. Let's compare normal then. So if you have an outcome, a random variable x with a sample space of the real number line, negative infinity to positive infinity, then the likelihood function for x is given by this thing, 1 over the square root of 2 pi sigma squared times e, or exponent, Euler's constant, 2.71, raised to the value in the parentheses here, the random variable value x minus mu of x squared over 2 times sigma squared x, and that whole term is multiplied by negative 1. Now you'll note here x is a variable. That's our random variable. So that means mu and sigma are parameters, and this pi is a constant. It's just 3.14, whatever, et cetera, et cetera. So pi is not a parameter of the model, it's a constant. So very much like e is a constant, although I write e out with exp. Okay? So those parameters go by names. We call mu the mean. We call sigma squared the variance. And it turns out in a normal distribution, mu and sigma are the only two parameters. So we also sometimes call them sufficient statistics, in that they contain all of the information we need to understand the shape of the distribution and the likelihoods that come from it. What that means in a normal or univariate normal distribution is the skewness, like how much the distribution leans, or how peaked versus flat the distribution is, are relatively fixed up to where the variance dictates at least the peakness. And the standard notation for this you saw before, x tilde n, and in parentheses mu and sigma squared. This is read x follows a normal distribution with mean mu x and variance sigma squared x. So normal distribution has a ton of nice properties. It turns out it's very easy to work with mathematically. So you find it in a lot of places in statistics. Um, the normal distribution also is sometimes what we call a limiting distribution, meaning as n goes to infinity in maximum likelihood, our parameter estimates converge in the distribution of our parameter estimates converge in distribution to normal. So it shows up, a lot of times people call that in nature more than just the convenience of picking a mathematically tractable form. The other thing I'll note is linear combinations of random variables that follow normal distributions. So a linear combination is adding variables together, sometimes multiplied by a weight, like a number. The result of that linear combination is also a normally distributed variable as well, too. And so normal distribution is everywhere. Multivariate normal distribution is everywhere, and it runs so much of what we do in statistics. So here's some more examples. These are three differing normal distributions. The blue curve, yes, I got this from Wikipedia. The blue curve is for a normal distribution of the mean of 0. So the center, the most likely point is 0, and a variance of 0.2. If we compare that to the red curve, which is a standard normal distribution, mean that mean of 0, a variance of 1, you'll see that the blue curve is more steep at a value of 0, right? But let's think about what it means. What is it? What is this? Let's take the blue curve for a second and describe what it means. So if I knew the mean was 0 and the variance was 0.2, and I had two values, two observations, I had a 0 and a 1. The 0 height is right here about 0.9. The 1 height is right here about 0.1. Again, 0.9 is not a probability. It does not mean we have observing a 0 with a probability of 0.9. What it means is that compared to observing a 1 with a height of about 0.1, that a 0 is like 9 times more likely to be observed than a 1, right? It's relative. Um, Likewise, these other two distributions are just changing the values of each of mu and sigma. So interestingly, in this week, to get you to learn distributions, we're going to pretend we know the mean and sigma, and we're talking about random variables x as if they've not been observed. But next week, when we go back to building maximum likelihood functions, the flip's going to happen. We'll observe data. We don't know the mean and sigma. So this distribution function that I'm describing today will end up becoming a likelihood function next week with respect to parameters. This is kind of neat, right? Wish I would have learned that in one of my first classes. How are we doing so far? All right. So to demonstrate how the normal distribution works, we're going to try it with a few values. All right. So the top two rows here are a standard normal distribution. We call it a standard normal distribution, meaning it has a mean of 0, variance of 1. That term standard really just means that, standardized. Um, the height of a 0.5 is 0.352. The height of 0.75 is 0.301. So you'd say that the 0.5 is much more likely to be observed, or slightly more likely to be observed than the 0.75 in terms of the height of the distribution returns. Similarly, you can plug in different values, get different heights. I will note on this that the values that you see here, you can get in Excel. There's actually have a norm dist function in Excel to do this, which shows you these slides are kind of old. But if you're in R, there's a function called dnorm. If you've ever generated random variables, random numbers, like I did in the very beginning of this lecture or this class today, you would have noted rnorm shows there. Well, rnorm and dnorm are part of the group of things dealing with a univariate normal distribution. And again, there's two parameters, the mean mu and the variance sigma squared. How we doing? So you've seen uniform, you've seen normal. How about chi-square? How many of you dived into chi-square much? Now, you probably computed chi-squares before. That's like an intro stat thing. Do you ever play with the distribution for chi-square? Kind of a mess. But let's see this mess. Um, the chi-square distribution, I'm just showing this to you to, again to get the idea of what likelihood happens to mean. Um, Sometimes the sampling distribution, the variance follows a chi-square. Sometimes the likelihood ratio tests follow chi-square distributions. But chi-square, um, the sample space or the support for a random variable is the positive number, so from 0 up to infinity. And the distribution function itself looks like this right here. 1 over 2 raised to the power, that's a, looks like a v, but it's a Greek letter nu. Nu over 2 times the result of this function gamma. This is actually a gamma function, which you can look up on your own. Uh, Evaluated at nu over 2. Multiply that by the random variable x raised to the power nu over 2 minus 1 times e raised to the power of negative x over 2. Of course. I don't know about you, but I put that on a tattoo in my back. That's how important that one is. Like normal, I'm getting ready to put on this forehead, right? It's a big forehead. It probably would fit normal. I'm sorry, I'm just joking. Maybe I'm not joking. Maybe I'm crazy. Anyway, I'm definitely crazy. So, chi-square, though, I put this up there because it's ugly. I don't even know. You can look up the gamma function. What's the parameter of chi-square? Well, gamma, remember, this gamma is not a parameter. It's a function. It's like a denote, like f of whatever, or z of something, or g of something. So the only parameter in this is nu. So chi-square has one parameter. And turns out if you take this and do the mathematical statistics on it, you can show that the mean is equal to nu and the variance is equal to 2 times nu. So this is a distribution that's very common in continuous distributions. It's very unlike the normal. The mean, this tells you nothing about the variance in the normal distribution. But in the chi-square and in most of the other continuous distributions that are well known, knowing the mean implies that you also know the variance as well too, right? Sometimes we call nu the degrees of freedom because we do use a chi-square to figure out a p-value, and we have to give the chi-square a degrees of freedom. But degrees of freedom are interesting because up until you get to mixed models, degrees of freedom are always integers, right? 3, 4, 5. Well, it turns out the parameter by the chi-square does not need to be an integer. So you could have 1.5 degrees of freedom or 1.6. And it turns out some degrees of freedom estimation methods like Satterthwaite in mixed models or Kenward-Roger or other corrections to Satterthwaite actually try to approximate the number of degrees of freedom based on how much dependencies in the covariance matrix. And that's where you will get degrees of freedom that are non-integer values, right? There'll be some decimal value there. But just note that that's okay because the chi-square doesn't care. Nu just needs to be some number, positive number. So here's a bunch of chi-squares right here. I'm just showing you this to tell you this. If I take, let's say, the chi-square with 1 degree of freedom, and I wanted to compare the likelihood of the value of 1 with the likelihood of the value of 2, the likelihood of 1, height of that is about, what, 0.25? The height of a 2 is 0.1, so you'd say, which one's more likely? The 1, right? And what you can see with this is as the parameter, this is k, but it should be nu, as the degrees of freedom increases, or the parameter increases, the shape of this distribution starts to go from this weird inverted parabola thing to something that's much more skewed, right? So what a chi-square tends to be is positively skewed for small degrees of freedom, and as the degrees of freedom gets larger and larger, it actually starts to look symmetric eventually. But that's less the point. So, questions, chi-square, distributions, any of that? Doing good then. All right. Then let's talk about marginal, joint, and conditional distributions, because this is another feature that shows up quite a bit as well. When we go from one random variable to more than one random variable, there are several different types of distribution functions. But the distribution function itself, um, well, let me just say that there's several different types. They're sort of defined by characteristics of. So let's first imagine a hypothetical example where I had some type of coin, like a penny, and I can flip it, and we know that X will be the outcome of the penny, right? And I'm going to restrict the sample space to heads and tails. I'm saying there's no chance I land the penny right on its side. Has anyone ever flipped a coin and had it land on its side before? Lingua, oh my goodness. You have magic. Let's go to the casino. But that being said, I'm going to respect that to zero, okay? So heads or tails for the penny. And not only that, it's a fair coin. So the heads is zero point 0.5, the tails is zero point 0.5, right? So those are the different values of the probability mass function. Let's let Z be the flip of a coin of a dime, right? So HD and TD are the two outcomes for a dime. Again, you can't be lingual, you can't land it on its side. Um, again, that distribution's PMF, probability mass function, has a probability of zero point 0.5 for heads and probability of zero point 0.5 for tails. So it's a fair coin, okay? So there are three different types of distributions I want to describe. A marginal distribution, which is the distribution of one variable, right? F of x for the penny or F of z for the dime, regardless of what happened on the other. All right. Alternatively, there's the joint distribution, right? And now that my cast is off, by the way, I didn't show you this. The cast is off. Hooray, hooray for me. I can do this now. I can take two coins and flip them at the same time. That flipping at the same time and looking at the two results would be the joint distribution. So basically, this is a multivariate distribution in that I have two random variables that I'm trying to describe how likely both events happen simultaneously. Okay? So marginal distribution in this case is univariate. Joint distribution in this case is multivariate. And then finally, right, if I had done this, maybe I'd, flip both of them. Again, flip both of them, maybe not sequential, maybe sequential, maybe not. A conditional distribution is what happens when I want to describe the distribution of one variable conditional on the outcome of another, right? So f of x, and we put this little pipe character in the middle, f of x type z is the distribution of x conditional on z, basically how the penny will land depending on how the dime landed. Similarly, we could describe the distribution of how the dime landed conditional on the distribution of how the penny landed, f of z given x. So when you look at this f of x line z, you say f of x given z. Okay? All right. So marginal distributions of what we worked with exclusively to this point. Those three continuous distributions were marginal, right? Marginal, it's possible to have a multivariate marginal distribution, but let's leave that aside for right now. In the context of two variables, a marginal distribution refers to the distribution of one of them. Okay? So similarly, f of x for the distribution of the penny is a marginal distribution. F of z for the distribution of the dime is a marginal distribution. Now, a joint distribution is the two variables simultaneously, right? So joint distributions describe the distribution of more than one variable. I just said that. So commonly, the joint distribution function is denoted with all random variables separated by commas, right? So f of x comma z, we'd say the distribution of x and z, which is different than saying the distribution of x given z, or the distribution of x by itself, right? So the distribution of x and z, why we say it that way is to make you think, to get a likelihood, I can't just give the value of x, I actually have to give both values, x and z, to get a likelihood, right? So at x and z, if both are discrete, like in our example, there's four possible discrete outcomes that show up. Both the penny and the dime are heads. You have that's number one. Second one is heads for the penny, tails for the dime. The third one is tails for the penny, heads for the dime. And the fourth one is tails for the penny, tails for the dime, right? Each permutation of how the coins can land. So joint distributions, by definition, are multivariate distributions, meaning, again, you have to observe each one of those values to get the likelihood. Okay? So we're going to use joint distributions to introduce two topics. This is where we're headed. Joint distributions of independent variables, which is this example. I'm saying nothing about saying both coins are fair, so they shouldn't be related in how I flip my coins. And then joint distributions used in maximum likelihood distribution estimation. The other thing I'll add to that in the context of missing data is how we can frame a joint distribution and have it be equivalent to the product of a conditional distribution and a marginal distribution. What I mean by that is, you remember the example I showed you last week with IQ and job performance in Levon? And I said, oh, I had to estimate this as a joint distribution. And instead of having a regression slope, I had a covariance. That was me allowing X to be part of the likelihood itself, which gives me missing data protection, missing at random assumption. So knowing a little bit about how joint distributions map onto marginal and conditional distributions to give the same result is important. Okay? Okay. Let's see here. So this is the joint distribution of independent random variables. This is the example with discrete variables here. Random variables are said to be independent if the occurrence of one event is neither, it makes it neither more or less probable for the occurrence of another event. So mathematically, that means we can express the joint distribution of x and z as the product of the marginal distribution of x and the marginal distribution times the marginal distribution of z. So remember, f of x, what does it return? It's the height of the distribution of x. In our case, it's a probability of heads, right? Or whatever x happens to be. And z is the height of its distribution. So the product of those two is equal to the height of the joint distribution when the variables are independent. And so for our example, flipping the penny and flipping the coin are independent. So we can actually build this contingency table of dime and penny, and the four values in the center of it come from taking the product of the margins, right? So the distribution, when we want to take the height of the time when when the penny is heads and the dime is heads, we'd multiply the likelihood of the heads for the penny or the dime times the likelihood of the heads for the penny, and we get this value here in the middle. And you could do that for each of the four cells, taking the margin, literally where marginal comes from, the margin, and multiplying the product of the marginals for each of the respective cells that go through that table. How are we doing? All right. So this is what happens. This is the product, right? So I mentioned before, f of x and z is equal to f of x times f of z when they're independent. So here, this is f of x and z, which is really f of x times f of z for each of these cells. And if we were to plug in those values based on our probabilities of our margins, you'd see each possible permutation of heads and tails on the dime and penny is equally likely, or each has a 25% probability of occurring. Right? Another way of putting it is those values, because they're all the same, because they're equally likely. Where did you hear that term in this lecture? What other distribution did you hear it with? Uniform distribution, right? That's right, uniform. This is a different type of uniform, right? This would be called a discrete multivariate uniform distribution. Discrete meaning there's only four possible outcomes in the sample space. That's different than the uniform that we saw before, where this segment of the real number line technically has an infinite number of outcomes, but it's bounded within the range A to B. Right? So this is a discrete, and then the term multivariate meaning it's a distribution of two variables, x and z. Discrete multivariate uniform. By the way, both x, the marginal distribution of x is discrete uniform with one variable, univariate. Okay, moving forward. So we can go from a joint distribution. So what we did here in this example is we took the margins and we built the joint. And usually that's impossible to do. The only way we can really do that is if we know the marginal distributions of if x and z are independent. Right? And in this coin flip example, I'm going to tell you that's the case. Right? We have to assume that's the case. It's usually the other way around. X and Z have some type of relationship, so we have their joint distribution, but we may want to get to a marginal distribution. And to do that, it's like saying we have the center of this table. How do we figure out the margins on the outside? So in the discrete distribution, you'll note each margin is the sum of the joint for each column or in each row. And that's what we're saying here. F of x is the sum of the joint distribution across all values of z, right? So the marginal distribution for pennies is the sum across each value of z for every level of x. Make sense? Now, sum in calculus is the symbol that we do when we have discrete measures. When we have a continuous distribution, marginalize is found by taking an integral across the distribution function. So f of x and z is a PDF for x and z. Both x and z are in the formula somewhere, just like we saw for chi-square, normal, univariate, in the continuous distributions. But if we want to get rid of z, we have to integrate that joint distribution with respect to z. Right? So basically, that's what this says. So an integral is like erasing z. Basically, it's weighting x by all the likelihoods of z itself, of the area under z. How are we doing so far? So yeah, question. Yes, the integral being the eraser. Yeah. So think of it this way: if I have this distribution that's both x and z, but all I really care about is what x is doing by itself, I need to remove z from that equation. So what I end up doing is taking the integral of the equation with respect to z. And what that does is sort of remove z from the equation altogether. It expresses x only as a function of x by itself, and the influence of z is no longer there. Now, it changes values of things, and in many cases, there's no closed form solution to what it will be. This integral is complicated, takes a lot of training in calculus to see patterns, or better yet, maybe ChatGPT can do it for us these days. I don't know. ChatGPT used to be a TI calculator, and when I was in calculus, where you could actually get it to do symbolic integration. But that being said, there's a lot of symbolic integrators these days, right? We get rid of z. That's the main thing. Okay, that help? Got it. All right. Finally, conditional distributions. Right. So if you have two random variables x and z, a conditional distribution is written as this: the distribution of z given x. It turns out it can be formed by taking the joint distribution and dividing it by the marginal. And so what that means is if I have the distribution function from the joint and I've integrated or summed to get the distribution for the marginal, I can find the conditional by taking their heights and dividing them. Or if I really like mathematics, might be able to find a closed form of doing the algebra in this case of the division of these two PDFs. Although that I wouldn't advise it. It takes a long time. But take a look at this. This is literally a simple equation, right? One result is equal to the result from one distribution divided by the result from the other, right? The likelihood of one divided by the likelihood of the other. The likelihood of the conditional divided by the likelihood of the marginal. If that's true, we could actually do algebra on this. So what this implies on your screen is that if I wanted to re-express the joint distribution, f of z and x, if I multiplied both sides by the marginal f of x, I would say that a joint distribution is really equal to a conditional distribution, f of z given x, times a marginal distribution, f of x. And therein lies why I could have shown you what I did last week and have it be related to linear models. Last week, I showed you the regression of predicting job performance by IQ, but I did that as a joint distribution right here. If I put that into the LM function, it would be a conditional distribution, f of job performance conditional on IQ. Right? So I could make the result equivalent to a joint distribution if I had the distribution of x as well. Right? Well, it turns out by putting x into the likelihood and framing it as a conjoint distribution, I actually do assume something about x, and I actually assume that x followed a normal distribution, a marginal normal distribution. Why that's the case, you'll have to get to the multivariate normal likelihood in another week or two to get there. How's that sound? How's this doing for you? Yes, question. Hmm? So here I'm saying from a very first of all, conceptually, yes, I think you can prove this mathematically um, in your math stat class. And back in like 1998, I did, but that's also gone like semi-partial correlation, right? But conceptually, think of it this way: what is f of z and x? If I plug in z and x, I get a height. What's f of x? If I plug in x, I get a height. Both of those are numbers. I can divide them so long as f of x is not zero. I can create a division like this. So from a brute force sense, if I, for instance, if Ahmed, if I was in a Bayesian sense, I know we haven't gotten to Bayesian yet, and I know it's break time, but after this we'll take our break. If I wanted to calculate a joint likelihood because I wanted to think about, a prior distribution, but this joint was really difficult, well, the way I would do it is break it down into a component that's conditional, which I might be easier to get to, times a component that's marginal, which may also be easier to get to. And in the truncated normal sense, that's what I really mean by this. So from a needing to understand today, two things. Number one, take my word for it, mathematically this works. But number two, um, from a just the result of the distribution sense, it also is tractable from when you actually get the likelihoods themselves. Does that help? Great. Other questions on this before we get moving a little bit? All right, break time. Let's come back about 2:31, and I will resume the fun. For me, it's fun. It may not be fun for you, but I hope it comes across. This is fun stuff. These are like the atomic blocks of how we do all of statistics, and I really like teaching that. So, all right, be back in about 10 minutes. Thank you. All right. So, conditional distributions are found everywhere in statistics. General linear model, predicting y with a series of x, y, z, x, z predictors is a conditional distribution where independent variables, the x's, are conditioning variables of what we're conditioning upon, and y itself is your random variable you're predicting. Okay? All right. So you can see what I was just saying. The you can get to, excuse me, let me get to back this. The conditional distribution z given x is equal to marginal versus joint. You can actually see that here. The distribution of z, the probability in this case of z being a dime having a head, conditional at penny having a head. We take the joint distribution of dime and penny both being head, which is 0.25, divided by the marginal distribution of penny being head, which is 0.5. We end up with 0.25 divided by zero point 0.5, which is just 0.5, right? So here, similarly, the same thing happens for the distribution of z as well, for tails, given penny was ahead. So you can see that it's a really trivial example when it comes to independent variable stuff. All right. Any other questions on conditional, joint, and marginal distributions? So the other part of this, as I was mentioning, when we get to certain missing data methods, as we get into later on in the text, some joint distributions are really hard to form. All right. So, for instance, if you have z or x that's continuous and z that's discrete, there's no real easy way to make a joint distribution. There's no distribution function that easily works, right? So a lot of times what you end up doing is saying if z is discrete and x is continuous, you could basically model z with like a logistic regression, conditional x is the predictor, get a conditional distribution of z, and then make a product of that with a simple marginal distribution, say x follows a normal distribution, and come up with a joint likelihood from it. And why I say why that's important is think of it this way. If you've got missing data on x and missing data on z, you really can't get a joint likelihood easily out of it, but you may be able to come up with a product of margin and conditional distributions that achieves your joint likelihood, thereby giving you the full missing at random protection. Why I'm showing you this is not just because it appears in statistics and we have to worry about it, but this literally is in, I can't remember if it's chapter 2 or chapter 3 Enders talks about missing data through maximum likelihood by factorization. Basically, the conditional distribution z given x times the marginal distribution of x is a factorization of a joint distribution of z and x. And so we can use that property to simplify, potentially simplify, or to build an analysis strategy that fully protects for missing data. As you're seeing this, this isn't as simple as mean imputation. Let me tell you, right? You're probably thinking, what do I care about missing data? It should be fine. And now I bet you're thinking, oh, yeah, that could be a little more challenging. And it is somewhat challenging, certainly. And by the way, this is all for missing at random. You got missing not at random. Look out. That's the. I wish there was. What's the emoji? I don't know if I can do that emoji. That's a face emoji here. Question. Yes. This is a mathematical property of distributions. Put it that way. And so, um, so in an introductory mathematical statistics course, you actually can show this, right? You start to, um, we define a joint distribution here. We can go and then integrate with respect to z and get a marginal distribution, and then you can show through mathematical properties of expectations that this conditional distribution is equal to this ratio that you see. So it's sort of a like a mathematical exercise that you can, a theoretical exercise that you can end up driving if you end up going into more of the mathematical statistics. Did that answer your question? Thank you for asking. Other questions? Okay. So let's get into another topic that is somewhat needed. It's expected values, and more generally, something called the algebra of expectations. So when I say expected value to you, what's the thing that pops into your mind? Do you have anything that pops into your mind? But expected value is a very specific statistical term. Many of you've heard it. What's if I were to say, give me a one-word summary of what expected value is? You would say mean. Yes. What's the expectation of x? It's the mean of x. So so we call it the expected value. Um, so expected values are statistics taken from the sample space of a random variable. They're like weighted averages, right? So why we have to think about it as a weighted average is because if we have a distribution function, like that normal PDF, we wanted this expectation. Basically, we would take every value of x and weight it by how likely it is to occur, and that's an expected value. And I'll show that a little bit more detail in just a bit. The weights correspond to the heights from the distribution function. So PMF for discrete values, or likelihoods or densities for PDFs for continuous discrete random variables. The expectation notation is this: E of x. E in parentheses is a formula. So just think of it that way. Like in the normal distribution, one of its parameters was mu, right? And we call it the mean. Well, that's not by coincidence. It turns out if we do the math to figure out theoretically what the mean of that distribution it will be equal to the parameter mu. That's where the synonym comes from, in part. Um, so the actual statistic that's being weighted by the PDF, or the actual value of x is being weighted is put where x is. So x itself, this is saying I'm going to apply something. I'm going to take the distribution function and do some other function of it. That's what it's indicating. And expected values helps us to understand what a statistical model implies about data. So, for instance, why a general linear model specifies the conditional mean and variance of a dependent variable, and we're going to see that in just a bit as well too. So, expected values are really important, but beyond that, turns out when we want to define the variance of a PDF of a distribution, it's also a form of expected value. So this function is somewhat generic, right? It's talking about we're going to take the value that's in the parentheses and weight it by how likely every value of it occurs in the distribution itself. right? So this sometimes is an x in the case of the mean. In the case of the variance, it's actually x minus the expectation of x squared, right? So now it's a function of something else. So this is a concept. So that's getting into what I call the algebra of expectations. So I learned that that term came from one of my professors in grad school, Rod McDonald. Let's describe expected value first. So for a discrete random variable, the expected value of x is the function, the sum over the space of x, the sample space of x, of x itself times the probability that x equals x. So this probability right here is another word for that is f of x, the distribution function, the probability mass function. So here, if my example is what is the expected value on a roll of a die? What's the expected number that should show up from 1 through 6? And we know that the numbers, it's a fair die, so every number is equally likely. It's a discrete uniform distribution, or has 1/6 chance of happening. This expectation is takes the value of the number that would appear up, in this case 1, 2, 3 numerically, etc., and weights it by the probability of that event occurring. Right? So it's like a weighted average. Right? Why is it a weighted average? Well, we're dealing with a hypothetical. We didn't observe x, we just hypotheticalized its distribution. This is what x should be in theory. So in theory, this is the mean of what x should be. And what you can see is that value is 3.5. Right? For continuous random variables, we replace the sum with an integral. Right? The integral is weighting each value of x by how much effectively area of an infinitesimally small window above x under the curve happens to be. Right? So the only difference between these two is that this is a discrete probability, whereas this is the actual PDF giving you that probability in the integral itself. But we're not going to be doing this. We're not going to calculate integrals. Just understand the concept. It's sort of mapping a discrete number. It looks like this. A continuous number looks like that. Okay? Turns out a variance I just mentioned is an expectation too. The variance of a random variable from a theoretical distribution is the expectation of the value of x minus the expected value of x, or written another way, x minus the mean of x squared. Right? So here, what we have to remember is this term in the parentheses is the term that's being multiplying the probability weights themselves. Right? So for the roll of the die, we just found the expectation of x is 3.5. So if we were to plug in each number, 1, 2, 3, 4, 5, and 6, into this x minus its mean squared, you see 1 minus 3.5 squared is the number that's now being multiplied by the weight. We run that through, we see a variance of 2.92, or similarly, the square root of the variance is 1.71, the square root of 2.92. How are we doing? So variances are expectations. Means are expectations, but they're just a different thing that you're taking the expectation over, right? And the word expectation really means it's what we expect to observe if truly the variable follows this distribution. Because what the expectation is this probability or this result from the PDF, 1/6 in this case, the PMF. Now, similarly, if I had a continuous distribution, this would not be the sum, it would be the integral, right? So instead of having x here, it would be replaced with x minus mean of x squared in the integration function. And then finally, if you have two variables, you can define the covariance between them as another expectation. Sound good? Right? So the covariance is the expectation of x times z minus the expectation of x times the expectation of z. And we know the latter two are the mean of x, the mean of z sometimes. So it's expectation of x times z minus the mean of x times the mean of z. And how you'd calculate x times z, again, would be if we had x and z here, we'd have the numeric value of x times the numeric value of z times its likelihood, or its probability in this case for the discrete distribution. So this gives you the mathematical specifics, but turns out there's some rules of thumb that you can come up with to quickly calculate expectations without having to do sums and integrals. And so I'm going to show that to you real quick here. And that's the algebra I'm talking about. So a linear combination of random variables A linear combination is a variable x created by taking values of, like this look like new, those are our random variables, multiplied by some constant, through n, right? So linear regression is an example of a linear combination, right? More generally, linear combinations of random variables have specific implications for the mean variance and possibly covariance. So if you want to create a new variable, and it's the linear combination of a series of other variables, you can come up with what the mean of the new variance happens to be, new variable happens to be, based on expected values of each of the components of the linear combination. So there are predictable ways in which these means variances and covariances are formed or change, and that's what we call the algebra of expectations. And to guide us through this process, I'm going to use an example where I had tried to predict somebody's weight based on how tall they were in inches. It's weight in pounds predicted by height in inches and which gender, male, female, they'll happen to be. Right. So this is the descriptive statistics I have here. Uh, I have a data set. This is in the R example that's in the folder that you see online. Um, the mean of the data set is 67.9. That's the mean height in inches. Standard deviation 7.44. I just calculated those using R. This is the simple mean and standard deviation function. And variance, by the way, is standard deviation squared, right? Or standard deviation is the square root of variance. Height 183.4 pounds with a standard deviation of 56. Whether or not a person was a male or female whether or not a person was female is zero point 0.5, so half the sample was exactly half happened to be people who were female. Standard deviation 0.513. Now, and below this, you have let's take a look at the bottom triangle of this matrix. This is the correlation between height and weight, the Pearson correlation between height and female, and the Pearson correlation between weight and female. This, by the way, is a point by serial correlation, calculated with Pearson, basically. The diagonal represents the variance of each of these variables, and the covariance is in the upper diagonal. Covariance is like correlation with a scale. Let me describe that a little bit more. Um, well, I'll get to that in just a bit. Yeah, I'll leave that for right now. It's tangential. All right, so, whoa, nearly fell off my chair. Come on, Templin. Wouldn't that be funny? Good thing my picture's not on Zoom, right? Or on YouTube. For those of you on YouTube, imagine me with the chair release. Just opened up and I nearly tumbled backwards. That's what happened. Okay, I'm not prone to falling or being clumsy, am I? Anyway, so here are some properties of expected values that we use a lot in statistics. So X and Z again are random variables, and C and D are constants. They don't vary, they're just terms, right? So if we wanted to add C to every value of X, right? So I'm rolling the die, right? 1, 2, 3, 4, 5, 6 are my values of X, and let's say I wanted to add 10 to it. What happens to the expected value? It turns out it's the expected value of X plus C is just the expected value of X plus the constant. Another way of putting it, we saw the mean of rolling the die was 3.5. If I add 10 to it, we know the mean moves up by 10, 13.5, right? The variance, though, is unchanged when I add a constant. So if I want to take the variance of X plus C, or my dice roll plus 10, the variance is still 2.92, or whatever it was a few slides ago, unchanged, right? So we shift the location by adding a constant, but not the scale, right? Variance is often thought of as scale. Finally, for the covariance, if we add C to one of the other random variables, like one of the random variables, X or Z, the covariance also doesn't shift. Just because we changed the location, you can think of a scatter plot in 2 dimensions. Just because we shifted where the center of the scatter plot is, doesn't mean we changed how wide the scatter happens to be in either direction. So that's where sums of constants comes in. So if we add a constant to something, the expectation doesn't change. I'm sorry, the variance doesn't change, the covariance doesn't change, but just the expectation. Now, what happens if we multiply X by a constant, right? So if instead of adding 10 to our die roll, we multiply it by 10. Well, you can imagine what happens then. Instead of having 1, 2, 3, 4, 5, 6, we now have 10, 20, 30, 40, 50, 60. And the mean's no longer 3.5, it should be commensurately 35, right? So it turns out multiplying x by a constant results in that constant times the expected value of x, right? That's where I got 35 from. If the mean of x is 35, then 10 times x gives me a mean of 10 times, sorry, mean of x is 3.5, then 10 times that mean is 35. The variance does shift when you multiply by a constant, right? That variance will shift by c squared, is multiplied by c squared. So before in my example here, if I multiplied each of my die by 10, the number that shows up at the top of the die by 10, my variance is not 2.92, it's 2.92 times 10, or 29.2. And that's because as you multiply by a constant, you can think if you plotted these values on the x-axis, it used to be 1 through 6, but now they're 10 through 60. And so because the range changed, the variance now has to change to be the same distribution on that range, right? Similarly, for covariance, multiplying x by a constant c and d by a constant or z by a constant d takes the original covariance and multiplies it by each of those constants as well. Right? Cool? Cool. Finally, sums of random variables. If I have a random variable x and a random variable z, and I multiply x by c and I multiply z by d, the mean of the new random variable and sum them together, right? This linear combination. The mean of that linear combination is c times the mean of x plus d times the mean of z. You can see where we're going here for regression now. Right? This is like saying beta 1 times x plus beta 2 times z, something like that. Similarly, the variance also changes, right? We knew the variance of a sum, of a weighted sum, a variance of a linear combination, is the weight of each variable squared times its original variance. So c squared times the variance of x plus d squared times the variance of z. But then we have to consider the covariance as well. And that's 2 times each of those constants, c times d, times the original covariance of x and z. How are we doing? You can see, by the way, that if you get this last term, if I were to ask you what's the covariance, or if I took just x minus z and I wanted to find the covariance of the difference between two variables, right? That fits into this. You probably know, if you've taken basic measurement classes, intro to measurement classes, this is finding the covariance between the sum of variables is important, or the difference between variables sometimes should be as important as well too. And in that case, um, x minus z really has c would be 1 and d would be negative 1. So what you end up getting is the variance of x plus the variance of z plus 2 times negative 1 times the covariance. Or another way we put variance of x plus variance of z minus 2 times the covariance. So if you know that well-known formula for figuring out the variance of the difference between two variables, this is where it comes from. Right? All right, let's take an example. Imagine that you wanted to convert weight from pounds to weight in kilograms, right? Where 1 pound is equal to 0.453 kilograms. You would just multiply a weight of a person by 0.453. We'd also see the mean weight for our sample would change. If the mean weight in our sample was 183.4 pounds, then it becomes 83.08 kilograms after we multiply by the weight. Right? The variance of weight in kilograms can work similarly, right? So we know that that would be 0.453 squared times the variance in weight. In that case, it would be 652.38 kilograms. And now the last one is covariance, and this is where it gets a little funny. You notice here I'm talking about the mean is in kilograms. The variance is in kilograms squared. If you remember, if you ever took chemistry or stoichiometry, there's a part where we talk about units and measures of units and how we may cancel units and so forth. Well, our variables are units. You usually have units, some type of units, at least in physical measures, but even Likert units are sort of rating scale points, right? And the same process that you knew in chemistry actually has a physical basis for what we do in statistics as well, too. If we take a square of a variable which is involved in a weight, it's in now units squared, right? Well, covariance is like a cross product of variables. It's involved in the covariance formula, right? We need the expectation of x times z. And that turns out that the covariance itself is in units of x times units of z. In our cases, kilogram inches. But the covariance, if we wanted to come up with it, we would take the covariance of weight in kilograms, right, which was 0.453 the covariance of times of weight in pounds, excuse me. There's our constant. So 4.453 is what we called C on the last slide. Height is multiplied by the number 1. We work that process through and we end up getting 151.68 kilogram inches. Ironically, kilogram inches is why we don't ever use covariance. Actually, kilogram squared is why we don't use variance. Because it's impossible, it's very hard to think of units squared. We think of area, yes, that works. But what are kilograms squared in concept? It doesn't mean anything, right? So if we took the square root of kilograms, now we're talking about the standard deviation, which is sort of the average deviation of an individual from its mean. That's what that stands for. And if we talk about covariance as in kilogram inches, do you remember how to get from covariance to correlation? Covariance divided by standard deviation. So the covariance of x and z divided by standard deviation of x times the standard deviation of z. So covariance is in kilogram inches. Standard deviation of x is in kilograms. Standard deviation of z is in inches. The units cancel, and we're left with a number that ranges between -1 and 1 that's unitless, but it's understandable. How's that sound? That's correlation for you. That's why we don't use covariance and variance very often, but there you have it. Why I'm telling all of this to you is because the choices that you make for model imply certain types of features of your data, and this is how you can sort of check that your model fits your data. And that's going to be increasingly important as we get into more advanced models as well, too. Maybe not so much in some of the linear model things that we get in this class, but certainly psychometric models. How are we doing? All right. Here's some R syntax if you wanted to do this yourself. You can see it all right here. And turns out in R, you may have learned the GLHT function. It will do the same. Um, I had a linear regression here. I don't know that I want to. Oh, here's the linear regression. This is, um, I was predicting a person's. Any of you done the mini golf homework in Lisa's classes? Ever taken that before? There's a homework that she created based on a hypothetical experience where I became hyper competitive against my sisters in miniature golf. Yeah, that's me. She didn't know me very well, but they hadn't beat me to that point in my life. I was like 30 years of kicking their butt, and they finally beat me. So it was a big deal for everybody involved. I was crying. I'm just kidding. But that being said, she created this homework where the outcome was your score in a miniature golf game. And you were put into a training group where there was a lot of training or a little training or some combination. I can't remember what it was. How much experience you've had in playing miniature golf, how enthusiastic you were about miniature golf, and then some interaction between the two. So if you wanted to come up with one of the estimates of parameters in linear regression, linear models with interactions, right? If we wanted to look at the simple slope of, group two, for instance, or simple slope of experience, we'd have to combine experience with group two's slope. So the slope of experience in group two, that's this linear combination. And that's what GLHT is doing. And you can use the algebra of expectations to derive it. I'm going to leave it at that. You can see it. The point I'm trying to tie here is this isn't just me playing with math stat when I'm doing all this. This has real implications for how we do statistics. And so if GLHT didn't exist, which it actually didn't because it's an R package, so you have to know that it didn't exist when I started learning R. Let's put it that way. So what you had to do is you actually had to go inform what that estimate and standard error happened to be based on algebra expectations back in the old days. Thankfully, you don't have to do that anymore. But there you have it. That's why it is what it is. Okay. How we doing? So that's the beginning of the general linear model. Let's go a little bit further. Remember the general linear model, predicting y from x and z. You might have an x, beta 0. So y for a person is equal to beta 0 plus beta 1 times x plus beta 2 times z plus beta 3 times the product of x and z, the interaction. And then we have an error term, residual term, e. So in terms of random variables, e is considered a random variable, right here. So e is said to follow a normal distribution with a mean of 0 and a variance of sigma squared. And technically speaking, this is identically independent and identically distributed as normal. That IID, independence, if observations have some type of dependency, that's why mixed models or multi-level models exist. And if observations are what we would say are heteroscedastic, that means they wouldn't be identically distributed as normal, right? We would have to have some other type of function of variance to describe that distribution better. But that's why we have the assumption of homoscedasticity of errors in linear models. Literally right here, we wrote it down. Okay. So y is dependent, yp is dependent on the linear combination of x, z, and error, and technically the product of x and z. So what that means is y itself is basically what the GLM is providing is a model for the conditional distribution of the dependent variable y, where the conditioning variables are the independent variables x and z. And you'll note when I specify it this way, I'm making no assumption about their distribution, right? So what I would say is there's no marginal distribution of x here, and there's no marginal distribution of z here. It's just y is conditional on x and z. I'm not doing anything else. The slopes themselves are also thought to be constants in a frequentist point of view. Now in Bayesian, we start to give those distribution, but let's stay frequentist for right now. It's a little bit easier, right? That's why sometimes they're called fixed effects. When you get to mixed models or multi-level models, you will have slopes that are potentially random. When you get to Bayes, everything's random. So that changes a little bit of the math that goes behind this. So if we use the algebra of expectations and we wanted to find out what the mean of y happened to be, right? Y hat is sometimes described the mean of y. So y hat is the expectation of y. So that's actually the expectation of y conditional on x and z. So that's the expectation of this whole linear model, right? Beta 0 plus beta 1x plus beta 2z, et cetera, et cetera. Everything that I highlight in orange right there are constants. And so what we see about expectation with the constant, right? We can pull that out of the expectation function right here. Now, the expectation of a random variable, by definition, is its mean. And we define the mean of this random variable to be 0, by definition. So therefore, this term is 0, leaving us with the expected value of y being just what we get from our regression equation. And that is exactly why we call it our conditional mean of y. This shows up in we talked about this last week in conditional mean imputation, right? So what's the variance of y? Well, the same thing happens. Remember, everything in orange is a constant. So with the variance of y, we replace that with the model for y. Everything that was in orange, all the betas, those were constants. And what happened to the variance? When we added a constant to our random variable, it did not impact the variance. So we could rewrite the variance as just being the variance of e. And by definition, the variance of e is sigma squared e, which is actually an estimated parameter in maximum likelihood, usually is profiled or marginalized in least squares, and therefore you have it as sigma squared. So now we can see all those regression assumptions and how they tie into distributions and how we had to use expected values and distributions to get there. I think it's kind of cool, personally. So we just found the mean, expected value, and variance implied by the general linear model for the conditional distribution of y given x and given z. The next distribution is the next question is then, okay, so we found its mean, we found its variance, but we said nothing about its distributional family, its shape, right? So how do we figure out its distribution? Well, we have to go back to the model itself and think about the linear combination, right? And think about what I had said before when I mentioned the normal distribution. Linear combinations of random variables that are normally distributed result in variables that are also normally distributed. So here, because E is normally distributed, and it's the only term that's random in the model, right? All this is a constant, and E is normal, right? Basically, we know the distribution of Y given X has to be normal then. So if the distribution of Y given X and Z is normal, its mean and variance have to be what we just found by algebra of expectations. The mean of Y is Y hat. It shows up in our normal distribution as its mean. The variance of Y is sigma squared E. It shows up in the variance spot of normal. And there you have it, right? What I really wanted to get to is this. This is why we sometimes draw these sideways normal distributions with a regression line through it. Now, this top graph right there is terrible. That is definitely from 2012. I should probably replace that. Bottom one's a little better, but still not the mean. We want the mean to be at the peak of the normal distribution. I can get better graphs. That being said, what we're saying is conditional on X. What this is, if you condition, so Y in this case is widgets and X is foam board test, whatever the hell that means. Um, the distribution, you take a value of X, its distribution will have a mean right on the line and a variance equal to sigma squared. And that would happen for any value of X that you pick. And the same thing happens if you have X and Z. It's a multivariate distribution, or you plug in X, plug in Z, the distribution of Y is the same. Right? So how are we doing with all this? Making sense? Probably seen it before. If you haven't, that's great, no problem. If you have, I'm sorry, maybe you can teach it this way, or maybe you can not teach it this way. Learn from my mistakes, right? Don't slip on ice, don't teach it this way, that type of thing. All right. So treating our estimated values of the slopes and the residual variance as the true values, right? No, these distributions change when the sample estimates are used, right? So if we were to actually think of these as true, we could come up with a distribution for what a person's height, given whether they're weight or female, looks like, right? So if we had somebody who's 62 inches tall, and someone who declares themselves to be female, um, the mean of their distribution is 127.5 pounds, right? With a variance of sigma squared. Similarly, if we had somebody who was 76 inches tall, 6 foot 4 inches tall, and declared themselves to be a male, their mean was 248.0. This is where your first indicator of these data probably are a little weird. It's probably a little high for, well, we are in the United States, and if you, we should probably control for like which country you're from or whatever, because we're somewhat of a large population, but shrinking. Obesity rates went down this year, hooray! But that being said, a bit large. So again, this is a hypothetical example. If you really want to come up with a prediction interval, you have to go and think about more of a finite correction to it to allow it to be a bit wider. But if this were truly the numbers, this is what we would get from our analysis. And how I did this behind the pictures, I built this up by plugging in the values of each of my numbers. This is part of the reason, actually, why if you took Lisa Hoffman's class, she described the model for the means as being comprised of the fixed effects and the model for the variance as being something with E or something else. That's where that shows up. It literally describes part of the distribution of normal. All right. Now, if you wanted to check for normality, I don't know why you would, but I'll just throw these in there just for fun because it may matter at some point. Um, so you can see I use SAS. I didn't change this. Should be R. Anyway, the assumption of normally distributed variables is everywhere, but you can test them. There's several methods that are out there. There's actually millions of methods out there. This has been an age-old problem of making sure that your data follow a distribution of some sort. I'm going to pick two and describe a couple of them. One being, actually today I'm just going to talk about QQ plots, quantile plots. It's not like any of this is easy. It's no. You can never definitively declare your data to be normal or not, but it's one way to start. A QQ plot is where we take quantiles of our observed, in our case, residual values, and compare them to quantiles like of a normal distribution, right? So if the quantiles match, you say, oh, they should be the same, a theoretical normal distribution, right? So this is what it looks like. If we take the plot function of a resultant LM, this plot on the right, the dashed line is where the theoretical quantiles and our standardized residuals should overlap. If we have a normal distribution, you can see not all the points fall on a line. That's going to happen in a sample of data. It's just what happens. So um, and this is where you start saying, oh, is that an extreme deviation? Do I need to make some type of transformation or change my model? But that's part of regression diagnostics. And here's another example. This is non-normal data. This is really bad, right? There's our line where we want everything to line up with, and those circles are our observations. Has anyone ever done a QQ plot and seen something like this before? I would say this is a value where, see, we have our observed value here. It does not go below zero. So this would be a truncated distribution with a mean that's likely somewhere on the lower end. So what that would mean is if you use a normal distribution and you're truncated at zero and the mean gets very close to zero so much that the variance would overshoot zero, you see something like this. So oftentimes this is in this type of this is a QQ plot of credit card debt in thousands. Not a great topic to talk about. I guess better than talking about going to the dentist, but maybe I don't know. Anyway, um, that is something that where you might want to consider a variable transformation, perhaps, right? Or a different type of error distribution. Similarly, there's a Shapiro-Wilk normality test that works as well. You can apply that to residuals, and you can see if this p-value is low, then the data do not come from a normal distribution. But again, this is fraught with error. The sensitivity of this test is quite high, so you can actually have very minor deviations from normal, but have if you have very large sample sizes that are significant as well. Anyway, that's it for today. Um, Again, as I got into the book and I started going down chapter by chapter, I feel like these are important concepts to understand when we get to maximum likelihood, which starts next week, right? And so everything that starts in chapter, and so in the book, I'm having you read. I had you read chapter 2 before today, and chapter 3 before next week. Chapter 2 is maximum likelihood estimation. Chapter 3 is maximum likelihood estimation or missing data with maximum likelihood. What you'll see when you get to chapter 3, hold off for a few weeks because we're gonna talk about likelihoods next week and how they work, and then we're gonna talk about building things in Lavon the following week, and that's where the completion. So what we're going to talk about in the next 2 weeks is really what the end of chapters 1, 2, and 3 end up having. But to get to how likelihoods work, I really want to describe to you how distributions work because we're going to use that. That's going to show up many times in what we do. And I get a sense like missing data to do missing data well, it's almost like an engineering problem, right? It's almost impossible to go, hey, Chat GPT, I got missing data, make a model for me. Yes, I know I'm picking on Chat GPT. I use it too, but how many of you? I used it yesterday for a truncated normal, and it completely didn't work for me. Have you had that happen? It's how it's going to work for you for missing data. My guess is too. Now, eventually, our AI robot overlords might win, or we might get DeepSeek to do better than ChatGPT. I don't know, but it's coming. So, questions on anything from lecture today before we head out? Yes. Right here. So you're talking about you can understand the top one, is that right? But not these ones below. Okay, yeah, yeah. So think of it this way: if we go back to our algebra of expectations, the expectation of x plus c is really the expectation of x plus just the constant itself. So here, what we have to see is if beta zero, if this everything that's underlined in orange here is a constant, if I sum them all together, it's like the c in that algebra expectations. So when I take the expected value of this, they all become outside of the expectation function. Does that make sense? Yeah. And then what's left over, the expected value of error is set by definition in our model assumption. So it's set to zero, so that goes away. So that's for expectation. Let me show for variance. Similarly, if I go back to the algebra expectations for variance, all right, here I have that constant plus x. What I know is the constant disappears. So similarly, when I look at this constant's in the part that's in orange, all the betas and the x and z's, that goes away, leaving me just with I need to define the variance of error. And again, we define that in our assumption for the model as well, and to actually parameterize it, put it forward. Does that help a little bit? Is that what you're asking? You're welcome. Similarly, yeah, go ahead. Go ahead. Similarly, I could have defined this function a little bit differently. I could have said the expectation of x plus c is equal to the expectation of x plus the expectation of c. But because the expectation of c is zero, that would just become c. So if you wanted to think about if I pass this expectation through each part, almost like factoring an equation in algebra, right, where you have to apply a function to every component of an equation, you can think of it that way too. So that was the additional context. You had another question. Yeah, that was me kind of splitting the difference. Sorry about that. So the next quiz is still on what you read for chapter two. Technically, chapter three's quiz will be the one following this. And the reason for that is when you get to chapter three, you'll see it involves Levon and actually applying maximum likelihood, and we're not there yet. But I wanted you to read ahead a little bit. So technically, you don't even have to read chapter three before next week, but I put it there just in case you wanted to get ahead on reading. But the quiz will be about chapter two, part two. Okay. Thank you for clarifying, Vladimir. Anybody else with questions? Thank you. Yes. Yes. So I did not calculate it. I could probably find it by taking these regression weights, but I didn't calculate it. But I'll show you this though. Sorry, I was trying to provide some context. I don't actually have that in my head. One of you may. But watch this. If I change this to 0 times y, guess what's going to happen to what I do? My value gets very close to 0, right? So um, mainly because x does not actually predict y, right? And x1 and x2 don't actually predict y. So anyway, it's I'm sorry, I don't actually have the answer for you as to what it would be, but the answer does exist. And if you'd like to try to figure out what that happens to be, I'm happy for you to try that. But I don't have it for you. But it is related. Sorry. That was me saying, yeah, that's 30 years old in my head. I'm sorry. I should do better, but I hope I gave the context at least okay, Aikyung. Um, but if you want to if you figure out what it is, if you tell me that next week, if you want to, you're welcome to. But you don't have to. Okay? Yeah. Sorry, everybody. That was Akyung's gonna she knows when I'm like, yeah, I sort of glossed over that. I'm sorry if you want to know it, but it is there. I mean, it's one of those things. So I apologize. I apologize to you for that. Actually, if you want to know what it is, oh gosh, this is dangerous. If you go back to the equation, I don't have my slides up, and it's going to take me a bit to find them. If you go back to the equation, the slides for the semi-partial correlation, that was a function of the correlation between um, y and x1 and y and x2, and then x1 and x2. I believe you could probably figure out what this would be as well too, what that correlation should be. It just you have to add more terms to that function to be able to do it. And this here you can convert into correlation in a way. Okay? Ugh, sorry about that. I should have done it differently. Okay. Other questions? I feel like I let you guys down again. It's the end of class though, so you'll have to live with that letdown for another week. Sorry, it's all awkward here. I'm glad you said that, Ahmed. Thanks. Yeah, I feel like if I would, this is where we wanted to position this type of class early on, because to me, this is the modern version of multivariate. Multivariate statistics is no longer multivariate ANOVA. If you're doing multivariate ANOVA, they're better methods. Mixed models will do it better. All right. But multivariate statistics very much applies to joint distributions, likelihood functions, and other things. And next week, we're going to build a multivariate distribution uh, and then convert it into a likelihood function. So, all right, everybody, have a great afternoon. Again, you know what I'll do? I will come up with the answer for what the true value of y will be by next week because I feel so like I disappointed you and I don't like doing that. So I will have an answer for you next week. Okay? All right. Thanks, everybody. Have a great rest of your day. It was great to see you, and hopefully next week we'll be in person. Take care.